It's been really lovely to be here at Monash. I've had so many great discussions, and I'm excited for the rest of my stay. So today, as Ilya said, I'm going to be talking about how we can use tidal disruption events to learn about the nuclei of galaxies. And so what is a tidal disruption event? Well, if a star gets too close to a black hole, it'll get ripped apart, and I'll show a simulation of that here. Star comes in, it's ripped at pericenter, and then some of the material will return bound to the black hole. Some of it will be unbound if their orbit is very eccentric. And it is this material that returns on subsequent passages and eventually forms an accretion disk that produces the flare that we actually observe. So why do we care about tidal disruption events? Well, apart from just being cool, we can learn a lot of things about the disrupting black hole and the star. So we can try to estimate the black hole mass and accretion efficiency. These are often super-Eddington accretors. We can also learn something about the stellar properties and dynamics in the very centers of the galaxy. And so more on why we care about that. First of all, it's very difficult to weigh what I'll call small supermassive black holes, which is maybe black holes below 10 to the 7 or so solar masses. And the reason for this is that we're essentially using kinematic measurements to get estimates of black hole masses, or measurements of black hole masses. And so we have to measure the rotation of the gas or stars close to the black hole. As this velocity is lower, it's just more difficult to take those measurements. And so if you look, for example, at the classic M-sigma relation, this is from McCollum-Moss 2013 paper, it's very well populated above 10 to the 7 and starts to fall off below 10 to the 7. And we actually expect more, the black hole mass function to potentially increase at lower masses, although it's quite uncertain. Of course, you can potentially see smaller black holes if they are accreting as active galactic nuclei. But it turns out that most massive black holes are quiescent. And so this is a bit of a complicated plot, so I'll just step through it. It's the relative number of black holes as a function of the black hole mass. And so if we first look at this number down here, this is the number of active galaxies as a function of black hole mass. And you have to multiply that line by 170 to match the line for all galaxies. So if all massive galaxies are hosting a black hole, we're only seeing less than 1% as AGN, and there's very large uncertainty in the low mass end, as I already mentioned. Now, TDEs are actually preferentially observable around small supermassive black holes. The reason being, well, part of the reason being simply that as the black hole gets particularly large, above 10 to the 8 or so, the disruption is occurring inside the event horizon, so we're not going to see anything. And this is a plot that's basically showing that. It's a theoretical estimate of a TDE rate as a function of black hole mass. And if you don't account for a direct capture, you get this black dashed line. And if you do, you get these rainbow lines. And of course, it depends on the spin of the black hole, but basically it's dropping off very sharply above 10 to the 8 for main sequence stars disrupted by a black hole of any spin. Yeah. And so we're actually already starting to probe this black hole mass function with TDEs. This was an early attempt to do so, where we have the optical and UV TDE rate on the y-axis and the black hole mass on the x-axis. And the theoretical rate is the dashed line. And you can see binned observations as black points. And they're already starting to drop off a lot above 10 to the 8. We get a lot of TDEs between a few times 10 to the 5, a few times 10 to the 7, very few above 10 to the 8. This was pretty small number statistics. There's been a more recent effort to specifically focus on this lower mass end where we're getting more TDEs to do the next thing, which is actually to probe the black hole mass function at these lower masses. And so this is what this much more recent paper last year tried to do with a bunch of new TDE observations. And so this plot is again showing a black hole mass function as a function of black hole mass. You can see 10 to the 6 here, 10 to the 8 here. And so the TDEs here are starting to extend out past what these other observations in the shaded lines are seeing at larger masses and probing down towards 10 to the 5 or so. And then the dash curves are extrapolations based on X-ray observations or nuclear star clusters where we don't actually know for sure there's a black hole, but if there was one, that's the sort of mass function that it would predict. We can also learn about stars in the central parsec of the galaxy, or the sphere of influence of the galaxy, because that's where TDEs originate from. And this is at size scales that we really can't probe directly outside of our own galactic neighborhood. And so this is made from data from the Galactic Center group at UCLA of our own galactic center, where we can very precisely measure all these orbits, which is super exciting. But we really can't do that for most other galaxies. And so being able to potentially learn something about a star that actually we know originates within the sphere of influence is another exciting use of TDEs. So hopefully I've motivated a little bit of why you should care about TDEs. But for the rest of the talk, I'm going to go first through some background of the TDE physics so that we're on more of the same page. And then I'm going to talk about how we can actually connect our understanding of the theory to observations, and then use that to put constraints on things like the black holes and stars. And so first, if we're thinking about TDEs, I often kind of split this into two parts. One is the dynamics that lead to disruption and the mass fallback rate of debris after disruption. And the second is the actual production of luminosity and reprocessing. And this second part is a lot more uncertain. So the first part, we'll go through the physics. It's relatively well understood. The second part, there's a lot of work to be done still. So what happened, how is a star disrupted? Well, here are snapshots of a simulation. The star comes in around the tidal radius, which is essentially a Hill's radius argument. The tidal force overpowers the self-gravity of the star. It's disrupted. Part of the mass is unbound if the disruption is very, very eccentric, nearly parabolic, which I'll show later is often the case. And then part of it will return to the black hole. And then we also define an impact parameter, beta, which is annoyingly the opposite of the way impact parameters are often described. So it's the tidal radius as defined up here, which is, again, like a Hill's radius, dependent on the masses and the radius of the star, divided by the pericenter radius. So as you go closer to the black hole, you actually have a higher impact parameter. So a little bit more about this disruption process to understand the physics better. If we take some numbers for a 10 to the 6 solar mass black hole, like the one at the center of our galaxy, for a solar mass star, the tidal radius is about 100 solar radii, but the radius of influence is a parsec, and so it's 10 to the 5 times larger than more than 10 to the 5 times larger than the tidal radius, which is why we expect most TDEs to be on very eccentric, nearly radial orbits. We can actually do a quick estimation of the angular momentum of these orbits to understand where the stars that are mostly getting disrupted are coming from. And so this is often thought of in terms of loss cone dynamics, which has been studied for a very long time now. Papers in the 70s and 80s on this, certainly for TDEs, where we can define the angular momentum just of a Keplerian orbit, which is reasonable except for the most relativistic disruptions. And then if we sub in the tidal radius as our pericenter, we can very quickly find that the angular momentum needed for a star to be disrupted is about 2 GMH RT, which is very similar, which is essentially the same as a circular orbit near the tidal radius. It's another way to think of it. And so how do stars actually move into this loss cone? Well, if we're talking about a kind of classic spherical potential, we think most of the rate probably just comes from two-body relaxation, so a random walk process. On average, velocity changes are going to cancel out. But then to determine where most of the stars are coming from, the flux into the loss cone peaks when these changes in the angular momentum per orbit are of order the angular momentum of the loss cone. So basically, when a star can pass into the loss cone in a single orbit, it's much more likely to get disrupted as opposed to taking many, many orbits. And this is where if you do much more complicated numerical calculations, like in this paper, the flux peaks. And it turns out that this ends up being at about the sphere of influence for the black hole masses in question. And this isn't going to be true for all black hole masses. It actually is further out for larger black hole masses. You can kind of naively think that as you increase your radius, you have many more stars. So the number of stars you can draw from increases. But then the changes in angular, you end up moving into this like empty loss cone regime where you've already disrupted all of the stars because because the changes in the angular momentum are so quickly disrupting the stars. So you're kind of at this boundary between where you're able to put more stars into your loss cone, but you still have a lot of stars in that part of the galaxy. And so very luckily for just remembering, it ends up being around the sphere of influence for the black hole masses in question. And you can estimate the rate. It ends up being about 10 to the minus 4 per galaxy per year. I'm not probably going to have time to go into this, but the theoretical observed rate, the actually observed rate that we're seeing is getting close to this, but it's still a little bit lower. We don't fully understand if that's just a selection effect issue or if maybe we need to be thinking of a more complicated dynamical picture like a non-spherical potential or various other things that you could get. But to first order, it seems to be, certainly within a factor of a couple, it seems to be working. So now I'm going to talk more about actually how we're producing the luminosity. So after the star is torn apart, I'm showing this same simulation as before, you get mass returning to the black hole. And this mass return rate, this fallback rate, which is what I'm going to call it for the rest of the talk, actually is very important for determining the amount of luminosity that you're able to get out because it's essentially the power source for the flare. And so mass that is most bound to the black hole is going to return on shorter orbits, and mass that is less bound to the black hole can return on longer orbits, and that defines the mass fallback rate. When I think about this theoretically, not just looking at the simulation, I like to break it into the mass energy distribution and the orbital energy as a function of time, because you can calculate the orbital energy as a function of time analytically. There we go. Whereas the mass energy distribution is determined by the hydrodynamics of the disruption in addition to the stellar structure. Before I go into more details of it, the mass that's going to return most quickly will be the mass that was on the outer layers of the star. So if you look at this disrupted star, you're going, this material returns first and was from near the surface of the star. And as you move towards the core or the disrupted core, that material is going to return last. And so if you've heard of T to the minus 5/3 fallback rate, defining TDEs, this is essentially where it comes from. It comes from the orbital energy timescale of the debris. So if you take the derivative of the Keplerian orbital energy, you get a T to minus 5/3 term. And so the mass fallback rate is proportional to the mass energy distribution times this. And so actually, you would only expect the mass fallback rate to reach T to the minus 5/3 once the mass energy distribution is relatively flat. But that happens at late times in the orbit. After peak, this is the mass fallback rate versus time. And so it peaks, and then at later times it starts to approach this t to the minus 5/3 decline. That comes out very easily from the analytics, which is nice. Now, the mass fallback timescale is also dependent on the mass of the black hole. And this is very interesting because that's one of the things that we actually want to constrain with TDEs. And we can see this if we look at the dependence of the most bound debris on the orbital energy timescale, the most bound debris to the black hole. So if we have our black hole, if it's on a perfectly zero energy orbit, so that's like parabolic eccentricity approaching 1, then half of it will be unbound, half of it will be bound. Oh, and go back first. And you can estimate the energy of the most bound orbit as just the difference in the tidal force between the center of the star and the exterior of the star. You do a little Taylor expansion and you get this relationship that goes as the black hole mass over the tidal radius squared, or the black hole mass to the 1/3 power. You can then plug this into the Keplerian formula for the orbital timescale. And what you find is that the time scale for mass to fall back is proportional to the black hole mass to the 1/2 power. And so basically, as you increase in black hole mass, you're spreading out your mass in orbital energy and in time. And so while the same amount of mass is returning, a disruption around a larger black hole will have a lower power mass fallback rate and potentially be a slower evolving light curve. And I'm just going to show this here by actually plotting the mass fallback rate for different black hole masses. This is for 10 to the 5, 10 to the 6, 10 to the 7, and 10 to the 8. And you can see you go from weeks to month timescales to all the way up to almost year timescales for 10 to the 8 solar masses. And so if we can constrain this mass fallback rate from our light curves, then we can estimate the black hole mass using the light curves. Now, there have actually been many hydro simulations of the disruption process to better estimate the mass fallback rate. They're pretty converged at this point, but these are some of the different things people have done. And I won't go into too much detail about them other than to just say that it turns out that the time scale of the light curve or of the mass fallback rate is most dependent on the black hole mass. GR can affect it if you are in a very relativistic limit, so more the impact parameter of greater than 10 or so in many of these cases. The mass and age of the star can also affect it if the star is very evolved. But for a main sequence star, for an impact parameter close to 1, just where we'd expect most of the disruptions to come from, the mass fallback rate is mostly dependent on the black hole mass. But what these simulations don't do is show how mass is converted into luminosity. And so there's been much debate over this, but to first order, we know that the debris streams are on these initially very eccentric orbits. And so to eventually circularize and form a disk, they collide, lose orbital energy. And it's this process of losing orbital energy that's actually producing the luminosity, because the energy of these events is essentially coming from the kinetic energy of the gas. And so if we want to think about where most of the observed flare's luminosity is coming from, one of the things we want to think about is how quickly material is going to move from very eccentric orbits onto more circular orbits, because the efficiency of converting kinetic energy or converting energy to mass into energy is higher at smaller orbits because the kinetic energy is higher. And so when I think of the circularization process, you can have the circularization timescale be longer than the fallback timescale. And this is a relatively old simulation now, but I think it really qualitatively just demonstrates what a long circularization timescale looks like. And also, I think Dan Price is on this paper, which is nice. So there's many orbits before you're losing much orbital energy. You can also have fast circularization, where you're almost immediately losing significant orbital energy on timescales much less than the fallback timescale. And so you can imagine in this second case, the limiting timescale is the fallback timescale because you're almost immediately circularizing, whereas in this case, it takes a really long time for the energy to come out, and so the limiting timescale is the circularization timescale. But we know that at least in some cases, we're able to get significant energy out quickly because we see these flares that are on timescales similar to the fallback timescale. And in fact, while TDEs were something that were theoretically predicted for a very long time and predicted to have this mass fallback rate that the luminosity might follow, one of the big surprises when they were actually observed is that we were finding them at optical and UV wavelengths. And so if you think of an AGN being bright in the X-rays, that's kind of what people are expecting here. But in fact, many of these events you don't see any X-rays for, and they're completely dominated by UV and optical emission. And so what we have theoretically thought of to explain this, and what has seemed to be confirmed by some observations, is that in many cases, you're going to have a significant amount of mass and winds and outflows surrounding the black hole because these are very super-Eddington events, because these strong stream collisions that circularize the material also throw a ton of material out surrounding the black hole. And so this is a more recent simulation showing the results of the stream collision. And so this simulation actually starts after streams collide, so it comes back, precesses, collides here. This is general relativistic precession, and that is something I should have mentioned earlier, has been shown to be very important for being able to quickly circularize the debris. So even though the general relativity doesn't have a strong impact on the fallback timescale of debris, the apsidal precession is significant enough in many cases to cause the debris streams to collide quickly. So I'm just going to play this simulation. And so after the streams collide, material immediately is thrown out, and you're able to pretty quickly start moving material to much smaller orbits and start to form an accretion disk. And so if we think of the different components here, we have our initial precessing debris stream and the collisions, which are going to produce some energy. We also have an accretion disk that's going to produce energy. But in fact, as I mentioned earlier, it seems like all of this is surrounded by an optically thick wind. And so at some point in this outflow, the gas is becoming optically thick to observations. And so actually what we're seeing with our telescopes is the evolution of the evolving photosphere radius, and we're not looking directly at the source of the emission. And so although simulations have shown that you can get energy from stream collisions, you can get energy from accretion, it can be difficult observationally to actually determine where most of the energy is coming from, which is important if you want to study super-Eddington accretion, for example. You want to know if you're actually looking at the emission from that was coming from a disk originally. And so one thing that people have started doing to better understand this are to do these end-to-end simulations where you actually start at disruption and go all the way to the formation of an accretion disk and the eventual observed luminosity. And so the stuff I was showing before was either just showing the disruption or just showing after stream collisions. And the reason that this hadn't been done for a while is because it's incredibly difficult. You're simulating orders of magnitude in size scales and time scales, but there's starting to be some groups doing it, including FITS here, who just showed us their very impressive simulation results here. And while there's still, I would say, a lot of discrepancy between these initial simulations, something that they all seem to be finding so far is that they are able to pretty quickly release significant energy through through the initial shocks and collisions, and also pretty quickly throw out a lot of mass into potentially optically thick winds and outflows. And so something that I've done is a lot less complicated than doing an end-to-end simulation, but much faster to run. And that's use a simple model that combines the fallback rates as a power source with an evolving photosphere while remaining agnostic towards the source of the luminosity, and use it to fit a lot of the observations that we actually see. And so what this found is that for many of these events, we're actually getting a luminosity that seems to follow the fallback rate near peak. And I say near peak because this was at a time when there weren't that many observations that had really early and really late time data. This is probably the best observed one of the sample. But what this means is that maybe at least for the light curves near peak, the light curve timescale is dependent on the mass fallback rate, and then we can potentially constrain the black hole mass from there. I'm not going to go through that again. But that's what we used our model to do, essentially. And we were able to get constraints on black hole masses from TDEs doing this. And so on your left here, I'm showing the same plot as before, the McConnell-Mott plot with our estimates of black hole masses from TDE light curves that also have velocity dispersion measurements that are kind of going off the plot down here. And then I'm comparing over here with a similar plot, but with black hole masses from AGN measurements so that they're actually in the same sort of mass regime. And you can see that for now, at least, it seems like for these events where it seems like the peak fallback, the peak of the light curve is following the mass fallback rate, it seems like we're able to do a decent job of constraining black hole masses. And this is really exciting, but it still doesn't actually tell us about the source of the emission. It doesn't tell us, for example, about the actual the forming accretion disk. And so there are other models that that actually try to model the emission either as an accretion disk or as stream collisions and see what they get. But the way that I like to think about this is not necessarily as a dichotomy between the luminosity coming from these stream collisions at large radius and the luminosity from the forming accretion disk, but actually as sort of a continuous spectrum. And so instead ask, at what radius does most of the luminosity come from? Because essentially, in either case, what we're saying is how much kinetic energy is available to be converted into luminosity. And so there are definitely factors of order unity in front based on what mechanism is producing the luminosity, but ultimately the energy reservoir is the kinetic energy. And so if we zoom in on this picture before, we have our accretion disk, which is of order the circularization radius, which is close to the tidal radius. And then we have our stream collisions at larger radii. And so as we move inwards, the efficiency is going to scale with v squared over c squared. You're increasing velocity. And so, of course, this is why black holes are such an efficient energy source, because material is moving close to the speed of light near the actual gravitational radius. And so I did some estimates of the efficiencies of the luminosities in the entire light curves, which are relatively, there's uncertainties with the stellar mass and the efficiency, but before I show you some of those results, I just want to define the efficiency I'm using here. And so basically, here I'm saying that the efficiency is just the total luminosity divided by the m dot c squared, while m dot is the incoming mass fraction. So this could really be broken up into multiple component efficiencies. You'd expect some fraction of the mass to be thrown out in winds. And then there's also additional efficiencies for the actual stream collisions or accretion disks. But I think this is a simpler way to look at the big picture and think about limiting cases. And so when I estimated the efficiency from these light curve models and compared the efficiency to what we would expect from colliding debris streams, This is what I found, and I'm going to kind of build this plot up, but first just explaining what we're seeing. This is that efficiency that I talked about before, the luminosity divided by m dot c squared, as a function of the approximate circularization radius, which we can get from the same models. It's basically 2 times where we thought the disruption occurred, 2 times the tidal radius for a given model. And the reason this is interesting, or 2 times the pericenter radius more exactly, is that we can use simulations of stream collisions to estimate what the efficiency from stream collisions is likely to be near the edge of the accretion disk. And that's what I'm plotting here. And so simulations tell us kind of what fraction of the kinetic energy in stream collisions is able to be liberated into, or is able to be converted to luminosity. And so what we're seeing on this plot is that this region up here is only really consistent with stream collisions within the size scale of the accretion disk. And then this gray region is around the accretion disk with uncertainties from simulations of stream collisions. And then this region down here is more consistent with emission from stream collisions outside the accretion disk. And so there are very large uncertainties on these efficiencies, which I'll talk about later if I have time. But it does seem like many of these events are more efficient than we would expect for stream collisions and are more consistent, or for stream collisions at large radii, and are more consistent with processes of forming this accretion disk, and therefore more consistent with, and therefore useful to be studied for like the formation of accretion disks in these super-Eddington mass fallback rate regimes. We can also compare, so I was comparing with stream collisions, we can also compare the efficiencies we estimate with other accreting black holes. This is a plot of efficiency versus black hole mass. The gray points are AGN. The blue points are the same TDEs as before. This is a line to show approximately what simulations predict for super-Eddington accretion efficiencies. And you can see where some of them are relatively consistent with that. Some of them are lower. But it seems like in at least some cases, this is pretty close to what we would expect from accretion from a super-Eddington accretion disk. And I should also note that, again, because of how I'm defining the efficiency, if you're losing a lot of mass and winds, then you'd have to kind of bump up all of the efficiencies as well. And so the next thing I'd like to talk about is kind of coming at the estimate of the efficiency from the other direction. The reason there's such large error bars on that efficiency plot is because there's a big degeneracy between the mass of the disrupted star and the efficiency. And so these are not actually 1 sigma contours. I did slightly lower likelihood contours from these model fits to show the degeneracy more easily. But you have efficiency versus stellar mass from front of some of these model fits. And what you're seeing is essentially a degeneracy along lines of constant energy, because while there are some small changes in the light curve that will mean you prefer one mass over another, it's still quite degenerate with the efficiency that you choose. And so it'd be great if we could constrain stellar mass from something else. And one of the things that I've been looking at recently is looking at how we might be able to use composition measurements from the spectra to better understand the stellar mass, which also potentially could tell us something about the age of the star as a second order effect. And what really got me motivated in this is that some of these TDEs showed interesting metal lines. So here I'm plotting 2 spectra of TDEs, and these are probably too small to see, but you can see there's some, but you can't see. There's some nitrogen and carbon lines and silicon lines in addition to like helium. And then on the right here, I'm plotting compositional abundances as through a main sequence star, where you can see that they are, you just get this plot will essentially change based on the mass and age of the star as you're going through helium burning, hydrogen burning. It will also change as you go through helium burning, but that's a shorter time period. And so in particular, we were interested in looking at the nitrogen to carbon abundance because this is a really good proxy for both the age and the mass of the star. And this has been done a lot in AGN, but not so much in TDEs, just because of smaller population. And so if you look, the y-axis of this plot has the mass of the star, the x-axis has the age of the star, and the color bar is telling you the nitrogen to carbon abundance of the material. And so as you go from pre-main sequence up to post-main sequence, you're dramatically increasing your nitrogen to carbon ratio. And what I'm actually plotting here is the nitrogen to carbon ratio in the fallback rate. So we went a step further and looked at that as opposed to just in the star pre-disruption. And we wanted to know if we could actually observe this effect. And so connecting an abundance ratio or a line ratio to an abundance ratio is not trivial. It's very dependent on the radiation transport, especially in a very dense medium. That's not necessarily in thermodynamic equilibrium, but it turns out that for UV nitrogen and carbon lines, and again, this has been done for AGN before, the ratio is mostly independent of the gas conditions because these lines have similar ionization potentials and critical densities. And so there's much less other factors that it's easier to convert from a line ratio to an abundance ratio. And so there aren't a ton of events that have these UV lines measured because it's hard to get UV spectra. But already there are 3 TDEs with nitrogen to carbon ratios greater than 10, which is actually pretty constraining if you look at what this means for what types of stars have to be disrupted. And so I've shaded this region on this plot where the nitrogen to carbon ratio is greater than 10, and you're essentially limited either to stars above 2 solar masses or very, very evolved stars above 1 solar mass. And it turns out that, and this might not seem very large if you're used to thinking about supernova, but for TDEs, if we think back to the rates, if you're assuming that stars are getting put on disrupting orbits through two-body relaxation, then really the population of disrupted stars should trace the mass function of the nucleus of the galaxy. And most of the stars in the nucleus of the galaxy we'd think are low-mass stars because that's what you get if you use even a galactic center IMF. And so what we found is stars with nitrogen to carbon greater than 10 make up probably greater than 3% of TDEs, but only 0.05% of the galaxy's stellar population. This is interesting because if this is in fact an abundance measurement, then it means that there's something unique about the stars that are getting disrupted or about the stellar population in the nuclear cluster. And so we thought through some potential explanations. For example, if you assume that you would potentially assume star formation is centrally concentrated, if you assume it's incredibly centrally concentrated and very top-heavy, more top-heavy even than you would necessarily predict from galactic center IMFs, then you can start to get numbers that are consistent with what you would expect from the current mass function. I'm just plotting here so you get an idea of why it's hard to find why we wouldn't expect that many higher mass stars. This is just a Krupa IMF in gray, relative number of stars versus the mass of the star. I'm only going up to 5 here, and you can see how much the relative number of stars dropped off. If you use a galactic center IMF, this helps you out, but not very dramatically. What helps even more is if you assume some sort of low mass cutoff. And that's essentially what we'd need to explain this purely through the star formation process. Also, this is the IMF, so it gets worse with time as the higher masses stars die off more quickly. It's also possible that there's some sort of stellar interactions that could change the current mass function apart from just normal stellar evolution. And And so there's been recent work showing that you can get a lot of collisions in the very dense stellar environment in the galactic center. And if for a lot of these stars, you're moving, your rate of collisions is high enough that you're likely to collide, but you're not moving so fast that you fully disrupt. And so you can make more massive stars this way. And then there's also a possibility that you could get very, very high abundance ratios of nitrogen and carbon through stripping higher mass stars, but this doesn't necessarily help your rates. Okay, so actually I'll just, so I think I'm going to transition from here to talk a little bit about some of back to light curve analysis and think about how things might be a little bit more complicated than we initially supposed. So I told you early on that in these light curve models, we find that the luminosity follows the fallback rate near peak. But what happens when we're no longer near peak? So the first population of TDEs were generally discovered pretty close to peak, and then they were only followed up for however long after they're discovered. But more recently, as it has now, many years have passed since we started getting good data, people have followed up some of these disruptions for thousands of days. And what they've found is that in many cases, this initial very steeply declining light curve starts to flatten out. So the early time is consistent with mass fallback rate, with what you might expect from mass fallback rates. The late time, however, is more consistent with a slowly evolving disk. And so this was one of the first papers that pointed it out, and they showed that if you just use a simple alpha model disk, you can you can get reasonable estimates, or you can reasonably match the UV light curves that people were finding. A more recent paper did this in more detail for the event that had the best data, and they used a slightly more complicated model, but essentially found similar results. But I should note that in both of these cases, they're fitting to UV data, and so it's unclear if it's actually disk emission, or if because you're not actually seeing like a classic X-ray spectrum that you might expect for a disk. And then also at early times, there's starting to be more data. So some of these TDE specific surveys have actually been able to catch light curves at very early times, and some of them are starting to show potential signs of some sort of early time delays. Some of them rise very, very quickly, similar to what you saw for the mass fallback rates. But for example, in this event, there's a kind of slow rise. Maybe that's what you'd expect from some sort of diffusion delay. If you can constrain that, you actually get a second constraint on the amount of mass that's fallen back, which is helpful, separate from the efficiency to break that degeneracy. This very recent event, this paper literally came out, I think, the last couple of weeks, finds this early time bump in the light curve that's pretty bright compared to the peak, and maybe could be from some early stream collisions or something like that if you have a more extended circularization process. And so we're finding all of this new data, so it's really time for us to improve and build upon our models. So it's great. And do some of the things that, for example, Fitz is doing, and more carefully model the physics, but there's certainly plenty to do. And I think I'm running out of time, so I'll just leave with the takeaways, which is that TDEs can teach us about the black hole mass function, they can teach us about accretion disk assembly and stars and galactic nuclei, and really importantly, as I kind of touched on at the end, we are dramatically increasing the number of TDEs that we have in our sample. There's currently maybe less than 100 confirmed events, but this number was 10 a few years ago. And part of this is just transient surveys that are finding tons more supernovae, are also finding tons more TDEs, particularly ZTF, because it's aimed for these very blue transients. TDEs are very blue. And then Vera Rubin alone is expected to observe thousands of these events. So really the difficulty there will not be finding the TDEs, it will be classifying them as TDEs, since the light curves will not be the same quality that you see here. So thanks very much, and love to hear if you have any questions.
Yes, and I don't know if you mentioned this, but how does the rate scale with the massive black hole?
Yeah, so that depends on what you assume for the potential. I think in the theoretical work that I was quoting before, the Metzger and Stone paper, I think they found it goes approximately as a black hole mass to the -1/4 power. So you would actually expect more TDEs around smaller black holes. Of course, if they're Eddington limited, then it's potentially more difficult to actually observe them. But yeah.
Yes, just looking at the physics of it all, circularization.
Yeah.
For example, I'm more of a planetary man, you have the Earth-Moon system. The two objects go on a circular orbit around the common center of mass. But in your case, black holes 10 to the 8th solar masses, and this little star is just a tadpole. Now, how the heck does it exerting itself and pulling the center of mass out to where it was? This black hole was right near the edge, so other I've lost.
Oh, I see what you're saying. I think that's just a confusing snapshot, I think. No, I think, are you talking about this picture here? Yeah, so this is maybe not the, okay.
I didn't see how those circles weren't centered on the black hole.
Yeah, that's just my bad for not labeling it better. I think I labeled it in the past one. This is the black hole. In the simulation, that's the colliding debris stream. It's not the black hole. So that black point is not accurate when it comes to it's not following the same, it's not colored in the same color bar as the rest of the plot. That's my bad.
Sure. Yeah. The other thing is that very important decay rate you had there earlier.
Mm-hmm.
You had Reese's name against it. T to -5/3. I've seen that before, maybe in supernovae. I don't know whether it was a Russian guy, Safronov, or it goes back a long way.
Yeah.
Whether it was Kolmogorov or Safronov.
Yeah.
That's been sitting around a while, and it's obviously a very important result.
Yeah, no, you're absolutely right. I just put those names up because they specifically were referencing TDEs, but you're absolutely right. That has been derived by other people as well.
It was nice to see it reappear, though, after such a long time.
Yeah, it's a relatively unique case where these were long predicted events, and then they actually were observed and followed one of the theoretical predictions. So that's kind of nice.
Nice result.
Yeah.
Okay, quiet. No.
That's nice. Thanks.
Sorry, as a non-astronomer here, the efficiency is basically the efficiency of converting mass into light, as far as I understand. Yeah.
Absolutely. Yeah.
So where does the rest of the energy go? You have efficiencies of what, 10 to the -2, 10 to the -3, whatever. So that means that 99% of the rest of energy goes somewhere. Where does it go? Into the black hole?
It could go into the black hole, certainly, if it for an accretion disk model. In many cases, because you're so optically thick, you actually have really strong adiabatic losses. So material, it's dense enough that you're advecting material, and so you get strong efficiency cuts there as well. That's probably the biggest source.
It starts out as kinetic energy, but then effectively you're reconverting it into kinetic.
That's true. As you transport the luminosity back out.
If I can follow up on the efficiency question, you mentioned super-Eddington accretion and one of the plots showing efficiency, but you were actually showing efficiencies of less than 10% when describing super-Eddington accretion. So 10% is sort of a normal, typical efficiency if you're just considering accretion from a slim disk. So why do you need to rely on super-Eddington accretion to get to efficiency of 10%? Yeah, I think this plot, if you go one.
Yeah. Sorry. Sorry, are you saying why? I mostly. Yeah. So I was mostly including this. I'm not sure if I fully understand. I just wanted to have it as a comparison scale, whereas like 0.1 is the often referred to, or yeah, as you said, often used as an estimate for like AGN efficiencies. But then if you actually had a much puffier disk where you are getting things like adiabatic losses, and you're probably some of the luminosity is lost to the black hole, then the efficiency drops down. So I just wanted to compare it there, but maybe I don't think I'm fully understanding.
Yeah, I mean, I guess I'm wondering why you're labeling super-Eddington. Why
Oh, sorry, super. This is just, I'm purely pulling this from simulation papers of thick disks. So they're not TDE specific simulations. These are just simulations of where they've just arbitrarily chosen some disk setup that has a super-Eddington mass accretion rate, and then they estimate the efficiencies out of it.
So previously asked about the mass function of a supermassive black hole. Can we also infer maybe from type of stars and anything else about maybe the slope of your caps, or like the structure of the central region?
Oh yeah, so to repeat the question, can we learn something about the actual density profile of the stars in the cusp, in the nuclear cusp? Yeah, we'd love to. So in principle, different cusps will predict different rates. So if we get really good, if we can, for example, get enough TDEs that we can break down the TDEs into like host galaxy types, then maybe we can, or maybe we can say something about it that way. For example, a lot of TDEs come from E+A galaxies and come from what seem to be centrally concentrated galaxies, or that's maybe a separate rabbit hole, but basically come from galaxies that appear to be fairly centrally concentrated. But the best we can do with HST is maybe look on the 100 parsec scale for some of these cases. So we're not really even looking close to the sphere of influence. But yeah, maybe with a larger population size, we'll be able to start to say this.
Follow-up question: Will we able to probe better with Ruby maybe of the statistics, or will we?
Oh.
There's something else missing.
I mean, you tell me. I'm not sure. Like, you could say something about the overall density, maybe some sort of average density from the rates, but if you really want to break it up, what I would probably do is try to look at the different host galaxies and try to say something about, oh, it seems like the rate's higher in this type of host galaxy versus others. People have done that specifically for this one unique type of galaxy where we see a lot of TDEs, and that might tell us something about the dynamics in that specific type of galaxy. But a more general statement on the steepness of the cusp, I'm not sure.
So maybe I could follow up on that. So you just mentioned E+A galaxies, right? So galaxies that have still A stars, which are right around the right mass range, given your comments about the relative abundance of nitrogen to carbon, right? So you're talking about 2-3 solar mass stars still being around and still being prevalent as sources of tidal disruption. And also being galaxies where you had some relatively recent galactic mergers, right? And so maybe pulling those things together, does it mean that maybe we're thinking about this whole picture the wrong way when we think that the presence of stars in the lost cone is dominated by two-body relaxation? The one, I think Yuri Levin likes to point out that the one galaxy we know best, our own, does not have a spherical distribution of stars in the galactic center. We have these disks of stars pretty close in, and the moment you have a aspherical distribution of stars, you can actually greatly enhance tidal disruption rates much more efficiently than two-body relaxation. Yep. So does it mean that it's the presence of these asymmetries in the stellar distribution that's also determining which stars are actually getting disrupted and which galaxies and which black holes dominate the TDE rates? So
to kind of give some background on what Ilya is saying, I skipped this slide in this talk for time, but we have seen one of the main trends in host galaxy type that we've seen is an overabundance of TDEs in these E+A galaxies, which are essentially post-starburst galaxies. So this plot is showing H alpha equivalent width emission versus H delta absorption here. And so as you go down in the plot, this is essentially a proxy for star formation. So there's higher star formation up here, lower star formation. As you go to the right, there are less young stars, more young stars. So if you're in this bottom right, you have a lot of young stars, but you're not currently star forming. And this is the E+A galaxy or post-starburst galaxies, where we have in red there are TDE hosts, and you see a lot more. And actually in blue you see the specific events that have higher nitrogen to carbon ratios. And this was one of the motivations for that project. And you see that they do not follow the general distribution of the galaxy. There are way more TDEs in this region. So something I didn't mention when I was discussing that last, as for an explanation specifically for the nitrogen to carbon ratio, that's one of the things that we thought might be the case when we first started this project. But as it turns out, even if you had a recent starburst, you still aren't increasing the number. When you think about it, you're not increasing the number of high mass stars past the IMF, which I plotted earlier. You're kind of limited by your IMF. So even if you have a lot of younger stars, yeah, you have more massive stars around, but it turns out that that alone is not enough to explain that, to be fair, very small number statistics, but to explain what we're seeing. But yeah, there could be other interesting host stellar nuclear dynamics.